is it possible to have it so that I can see? Oh no, that's fine. I can see it. Okay, fine. Okay, so this is work which I think Godofredo Yomi has talked about already in Rio. So you'll have seen a version of this talk, but this is my version. So it's joint work with Godofredo Yomi in Santiago, in Catholic University, and Aníbal Veloso in Yale. But we mostly spoke to each other in Chile. Okay, so what's the setting? So the classical setting, I'm thinking about shifts basically the whole time. So if you're given a shift and suppose it's a subshift of finite type on a finite alphabet, so I've got so on some, sorry, sigma contained in here. And if mu and mu n, I shouldn't really use n, but there you go, are in the space of sigma invariant probability measures, then mu n converging weak star to mu implies that the lim sup of the entropy of mu n is less than or equal to the entropy of mu. Okay, so let me just recall sort of what's going on here a little bit. But before I do that, can I just check? Can everyone sort of see what's going on here? This is okay. Yeah. Okay, great. So let me recall some definition. So I'm going to say, well, it's also to introduce a notation. So Pn is the set of n cylinders. So that is to say, I've got x0 up to xn minus 1. So that's all the space of all y in sigma, such that the y's and the x's agree up to n minus 1. Sorry, I'm running out of space there. Xn minus 1. Okay, and then, so entropy then is h mu is equal to the limit as n goes to infinity, 1 over n, some c in Pn mu c log mu c. Okay, as you learn in the first course in ergodic theory, maybe. So, for example, if you had alpha 1 minus alpha, so it's supposed to be an alpha, Bernoulli measure on the full shift on, oh, I should call it 1 2, shouldn't I really? On the full shift on 2 symbols, then, so I'll call this measure mu alpha, then the entropy of mu alpha is equal to, it turns out, minus alpha log alpha minus 1 minus alpha log 1 minus alpha. Okay, so in fact, in that case, in this family, entropy is continuous. So I'm going to abbreviate a lot here, sorry. So entropy is continuous here, but in general, it's not continuous. So for example, oops, God, sorry, it's one of the worst things about being chaired by Stefano is he has such beautiful writing, and I don't. Anyway, so in general,
Don't make fun of my writing, Mike.
I'm not making fun of it. That's beautiful. I mean, one of the great joys of coming to your classes. So in general, you can have entropy jumping up. So for example, you could have, so they can exist, so mu n in this space of invariant probability measures converging to, say, some mu alpha weak star. This could have, this could be, for example, formed of Dirac masses. And so that would mean that H mu n would have entropy 0, but this guy at the end would have entropy mu alpha. Well, it's this guy over here, so that's strictly positive. So you can jump up in the limit, right? That's what I'm trying to say. So, right, that's the standard situation. So I want to, so that's a finite alphabet, subject to finite type. So now let's consider instead an infinite alphabet and non-compact settings. So, this has been a topic of interest in, for example, some flows on surfaces. So, e.g., recent interest in geodesic flows on non-compact surfaces. And so there's various works. So there's Einsiedler and co-authors, of who there are quite a few, and also some work of my collaborator, which I therefore will mention, Aníbal Veloso. But yeah, there are various papers on this topic in that setting. So this is quite, I mean, sophisticated stuff. There's a lot of structure and a lot of very sophisticated tools. Well, but including local compactness. Okay, and so I want to, so that's supposed to say including, that word means including. So local compactness. So here I'm going to consider shifts. Now, of course, shifts are kind of easy to get your hands on in lots of ways. So I'm going to say countable Markov shifts. But these can be quite weird. So less structure, which can have less structure, is what I want to say. Can have less structure. Okay, so countable Markov shifts. This means the alphabet is n. So I'm looking for subsets of this thing here. Okay, so what I want to do is I want to introduce the problem in the countable Markov shift case through an example. Okay, and we'll see through this example how things can go wrong and get some kind of general idea about how you might approach this kind of problem. So here's my example, and I worked on this this example with Henk Bruin in particular a little bit, and it comes from one-dimensional dynamics, Feigenbaum maps, but I'm not going to talk about that. So what I'm going to do is I'm going to take a subshift in n to the n0, and I'm going to call it sigma SV, and it's SV for Stratman-Vogt, because they were the first people to look at this model, although I believe this model was suggested to them by Sebastian van Strien to look at Feigenbaum maps. So I'm not going to get into the geometry of this because the geometry is not very important in this talk. But topologically, what happens is you've got two full branches, and then the branches become non-full, and they go down like this, and they accumulate down there to 0. Okay, so I could draw this more carefully, but instead of doing that, I'm going to draw the Markov diagram, which explains what's going on. Okay, so if I index this guy, I'll call this guy x1, this guy x2. So I think about what happens to x1, which I'm going to call 1 here. Well, and I've got state 2, which corresponds to that interval there, 3, and so on. So this is a full shift. So 1 can go to itself, it can go to 2, it can go to 3, it can go to 4, right? So any point, so this branch here, when you iterate it, it covers the whole thing. So you can go everywhere. You can go to all the states. 2 is also a full branch. So it can go to 1, it can go to itself, it can go to 3, it can go to 4, and so on. It starts getting interesting at 3. 3 can go to 2, itself, and any state forwards, but it can't go to state 1, right? There's a gap. And similarly, 4 can go 1 step back, stay where it is, or go arbitrarily many steps forward. And that's the pattern from then on, okay? So this is the Markov diagram. And you could also think about this in terms of matrices. If you wanted to, the transition matrix would look like this, and so on. So this pattern of zeros starting up here and then ones and the rest of it. Okay. So, okay, you've got this model. In the setup, I said something about having weak star convergence. Well, is that the right thing to consider here? So question 1 is what topology to use? Okay, so usually in the, well, let's say usually, often in the non-compact case, you use the Vega topology, right? So the Vega topology would be mu n converges to mu if whenever you take a compactly supported function phi, then you get the usual weak star type convergence. So this is true for all compactly supported phi in C0 equal psi going from sigma into R compactly supported.
So I can ask you a question, Mike. So now you've used the interval case just to construct the shift. Now you're forgetting the interval case, right? You're just looking at the shift. Is that correct?
I am, yes. Thank you. Yeah, so that's a very good point. Yeah, I'm just thinking about this as a crutch to rest on.
Sure. Okay.
Yeah, I think mostly, and then I go to shifts, and yeah, so
Okay.
the shift. I'm thinking about shift topology, thinking about shift metric from now on.
Okay.
For pointing that out. Yeah. Okay. So normally in the Vega topology, you take a compactly supported function, and you want to make sure this happens. And if that's true, then you say that mu n converges to mu vaguely, if this happens for all phi in there. Problem is, if your counter Markov shift is not locally compact, then this set of compactly supported functions is empty. Okay, so if you're used to kind of just going to the Vega topology and using that, then this is a bit of a shock and a little bit scary. So just to say, in the counter Markov shift case, local compactness says that from any state, you have a finite number of arrows exiting that state. That's local compactness. And as you can see for this example, it's not locally compact because you have infinitely many arrows coming from each of these states. So in the local compact, in the non-locally compact case, Vega topology is not going to help us. Okay, so what do we do? I mean, there's quite natural things to do at this point, and although you could argue they're quite natural, Yomi and Veloso have some papers on this, or one paper in particular. So they propose convergence on cylinders. So what does that mean? Well, it means what it sounds like. So mu n converges to mu on cylinders getting a bit dark in St Andrews at the moment. We had a wonderful summer, wonderful spring, but suddenly now we can go out. The weather's got worse. Anyway, so convergence on cylinders if for each C in your set of n cylinders for all n, mu n of C converges to mu of C. Okay, so quite a natural thing to do. The result by Iomi and Veloso says that if the entropy of topological entropy of sigma is finite, then the set of sub probability measures, so this is supposed to be less than or equal to 1, is what this notation is trying to say. So mu sigma invariant measure and the measure of the whole of sigma is less than or equal to 1. If you look at that set, then this is compact in the cylinder topology.
Sorry, Mike, just a quick question. I'm not familiar with this kind of topology. So is there any kind of uniformity required in this convergence depending on the n or the cylinder, just as long as for every cylinder you have convergence?
Yeah.
Okay.
Yeah, so if you're locally compact, this kind of coincides with all the usual ways, the usual things to think about. But yeah, there's no uniformity here.
Okay.
Okay, and just to say that this space here includes the zero measure, which is important because quite often you end up converging to the zero measure. Okay. Right. Yeah. Does anyone else have any questions about this topology before I move on? Well,
so somehow this compactness has to do with the shift because the condition is the topological entropy of this particular shift, right? So topological entropy implies compactness of this. Okay, is this an obvious thing, or is this a non-trivial? Is this a non-trivial theorem, or is it obvious?
It's a non-trivial. It's a non-trivial theorem. If you have infinite entropy, then infinite topological entropy, then all kinds of kind of silly things can happen. Yeah, I'll come back to some kind of issue like that later on. Yeah, you can converge to funny things at infinity in funny ways when you have infinite topological entropy. Sure, Anibal will be able to say something more sensible about that.
Right.
Okay, so let me just also say for some notation, and well, to remind you that if you have a sub-probability measure, then the sensible way to think about its entropy is to first normalize it. So this notation here, this means this is the total mass. So this is mu of sigma. So you normalize it, right? You take mu over the total mass. Of course, if the thing is...
Sorry, Mike, it seems, can you focus? The camera is not very well focused.
Sorry, I'm worried about focusing on my hand, so I've turned off something.
Maybe that's what's happening. Yeah. I think it's okay now. Yeah, I think it's okay. Someone was saying. Okay, thanks.
Okay, right. So yeah, okay. If this is zero measure, this doesn't make sense, but then the entropy is just zero. But you normalize your measure. You look at the entropy in the usual way I gave in the previous piece of paper, and then you look at the entropy there, and then you scale that by the total mass again. Okay. Right. So why have I introduced this example? Well, it's because I want to look at the upper semi-continuity problem here. So example for upper semi-continuity. Yeah, that's the problem. I can fix it like that. Okay, example for upper semi-continuity. So what I'm going to do is I'm going to define a sequence of measures, and I'm going to show that they converge in a bad way somehow. Okay, so consider for each n the subspace, sorry, sigma of SV, coded by, you've got n plus 1, and you've got n plus 2. Right, so remember the transitions are, you can stay where you are, you can go arbitrarily many steps to the right, and you can go one step left. So if I just take this piece here, the arrows are like this. So I have almost the full shift, but I can't go from n plus 2 to n, right? So I could also code this at sort of n window with the corresponding matrix. Okay, so if I think about all the sequences formed of these three symbols, then they live in SV. And if I look at the topological entropy, which I'm not going to define, this is equal to log lambda 1 for lambda 1 equal 3 over 2 plus square root 5 over 2. Okay, so that's the leading eigenvalue of this matrix. And I'm just going to point out that this is approximately 2.6. Okay, so what I'm going to do is I'm going to let nu n be the measure of maximal entropy. So classical theory says that in this subject finite type setting, you have a measure of maximal entropy. So in particular, it has entropy equal to log lambda 1, right? The variational principle. So this is going to form part of my sequence of measures that I'm going to be interested in when I'm considering this upper semi-continuity problem. Yeah, I'm sorry about the focus thing. Okay, I can try doing it live like that. Okay, anyway, right. So that's one of my set of measures. And then the other set is, I'm going to let, well, the other set is 1. So is mu0 is going to be half Bernoulli measure on the symbols 1 and 2. So that's on 1 and 2, I have the full shift.
Excuse me, Mike, I'm a bit confused. What is the n here? Is this sigma n you're indexing by?
Yeah. So
what? Yeah.
So previously, I set up my example like this.
Yes.
So I have my symbol 1, 2, 3, 4, and so on. Yeah. So what I'm doing is I'm isolating a part of my, I'm isolating 3 symbols, so for example, I have 5 there. I'm isolating, so this would be sigma 3.
But doesn't this look the same, whichever then you choose? It always looks the same.
Yes, absolutely.
Ah, okay. So there's no dependence. There's no dependence on n in these. Why?
Yeah, there is, because this lives on the space. For example, sigma 3. This is the space of all symbols, all sequences which just have the symbols 3, 4, and 5 in them.
Oh.
Transitions are the allowed transitions given by the Markov diagram.
Oh, I see. Okay.
Okay.
So the measures are the same, but they live on different subshifts.
Yes, exactly.
Right.
Okay. So, so what I'm going to do is I'm going to form. Okay, yeah, right. And so this measure here has entropy log 2. Okay. So what I'm going to do is I'm going to form a new sequence from this guy. So I'm going to let mu n, so set mu n to be equal to half mu 0 plus a half mu n. Okay. So there's nothing special about a half here. I could have chosen a third and 2/3, whatever. It's not important. And I'm assuming that n is greater than or equal to 3. So this is going to be my sequence of measures. Okay. So, sorry, the light in this room is changing all the time. Right, so then h mu n, so this is going to be independent of n, but as discussed with Stefano just now, each of these measures lives on a different part of the space. Well, they all live on the symbols 1 and 2, but as n changes, they see more and more to the right in the Markov diagram. Okay, so we've seen how to compute entropy for subprobability measures. Also, hopefully you remember how to compute the entropy for measures which are sums of other measures. So, for example, to compute the entropy of this, I take the entropy of the normalized version of this and then multiply by the total mass of it. So that gives me half that, plus similar thing for that. Okay, so this is, if I take the half out, then this is approximately half log 2 plus log 2.6, approximately. And in particular, that's greater than log 2. Okay, so if I think about what mu n does as n goes to infinity, so remember I'm trying to look for upper semi-continuity of entropy, okay? So since mu n converges on cylinders to 0, right, and that's part of my mu n, that means that this part of my mu n's is vanishing, right? We have mu n is converging on cylinders to something I'm going to call mu infinity, but that's just going to be this part here, right? Sorry, this part here. The rest of it's going to disappear off to infinity. Okay, so I've lost half my mass. So let's look at the entropy. So remember, for upper semi-continuity of entropy, we were interested in the lim sup of the h mu n's being less than or equal to h mu. Well, if I look at h mu infinity, so as before, this is the total mass of mu infinity, sorry, entropy of mu infinity over total mass of mu infinity, and that's equal to a half h mu 0, and that's equal to log 2. Half log 2, sorry, half log 2. Half log 2. So what's happened here? I've lost half of my mass in this limit, but I've lost more than half of my entropy. Okay, so lost more than half the entropy. Okay, so that kind of seems, so remember, recall the usual thing is to say that the lim sup h mu n is less than or equal to h mu. Well, that certainly hasn't happened here. All of these guys have entropy on the left-hand side bigger to the entropy on the right-hand side. Right, so this is my mu infinity. Okay, so this fails. Okay, and it fails in a quite transparent way, hopefully, if I've set my example up in a reasonable way. So yeah, so I'm going to state the main theorem, but before I do that, does anyone have any questions?
Mike, it just seems, I guess, intuitively, you've lost exactly the entropy corresponding to the nuance, right? I mean, is that the way?
Exactly.
Yes.
Exactly. That's right. That's the way to think about it. And in fact, you've lost. Yeah, you've lost the amount of entropy corresponding to what vanished at infinity, which is kind of obvious. But this does fit into a theory. So define delta infinity to be the supremum of the lim sup n h mu n such that mu n converges on cylinders to 0. Okay, so I'm going to call this the entropy of infinity. So I'm aware there are different versions of entropy of infinity. This is my version. And in fact, most of them coincide. So what's this saying? This is saying that take a sequence of measures which converge to 0 on cylinders. And the right way of thinking about that is that the measure goes off to infinity, right? I mean, I've given a particularly straightforward example, but you could converge off to infinity in some kind of very complicated way in general. So you take measures which do that, and then you look at the lim sup of their entropies, and you take the biggest possible number you can get for all the sequence of mu n's going to vanishing off to infinity or converging to 0 on cylinders. Okay, and so here's a theorem. Okay, so this is not just for this example, this is a general case. So let this be a transitive, so topologically transitive countable Markov shift with finite topological entropy. Okay, so then if mu n converges to mu on cylinders, you have that the lim sup of h mu n is less than or equal to total mass of mu normalized version, and if this converges to the zero measure, you just neglect this first term, plus whatever's left over times delta infinity. Okay. So let's just unpack that slightly and then compare it to my example. So, for example, so if the total mass of mu is equal to 1, so which is say no mass escapes, then you have upper semi, the usual the classical upper semi-continuity standard upper semi-continuity of entropy holds, right? So I think I wrote up there. And so that's actually difficult. I mean, not a straightforward result to prove in itself. And we actually have a paper previous to this where we proved that. So previously proved in a previous paper on ITV for the ergodic case. Sorry, it's going off the end of the page. Okay, but this is more general. It holds in a non-ergodic case, and it holds also in mass escapes. I also want to say that the theorem is sharp I mean, it's sort of maybe obvious from the way I've set this thing up by defining it via the supremum. So what do I mean there? So for example, so if you choose mu n.
Need to bring the paper just down a few centimeters.
Sorry. Like that.
I cannot see the top, the line. I don't know if everyone else can see.
Sorry, yeah, whole thing shifted, yeah. Sorry. Thank you very much.
Yeah.
I think a bit skewed for some reason. Okay, so choose mu n in the definition of delta infinity. Namely, you choose some sequence here which essentially achieves this supremum, sort of in definition. So this is a bit sketchy, but so then if you look at the left-hand side, so if I call this equation here star, out of the left-hand side of star, well, if I choose something that's going to achieve that, then it's approximately delta infinity, right? If I just choose a sequence of mu n that almost achieves the supremum, I get that. And on the right-hand side, well, my mu n's are converging to 0, so this term on the left is null, and this is just 1 times delta infinity. Okay, so the right-hand side star is equal to delta infinity. So you can't do any better than this constant here. Okay, so there were previous, for example, there's some work with Einsiedler and also Kadyrov and Kapol, where they were looking at this number here and how they can improve it and what it means. Well, in our setting, it's the entropy infinity, and you can't put a better number there. Okay, I could also put this into my previous example, but maybe I'll skip that. Okay, so that's one version of the theorem, and then I want to give a topological version. But does anyone want to ask anything before I do that? Okay, so here's a topological version. So in fact, our work is principally in the topological setting. We do also counting. So if you define delta infinity top, so I'm going to define this in a moment. So I'm going to let little zn, this is a bit like a partition function, a number of cylinders x0 up to xn plus 1. The indexing here is a bit weird. Such that x0 and xn plus 1 are less than or equal to q. So q's here. So I think of q as being quite a big number. And the number of terms in between those, such that xi is less than or equal to q, is less than or equal to n plus 2 over m. Yeah, and again, I apologize for the funny choice of indices here, but what I'm trying to say is I'm starting, my first symbol is less than or equal to q. So I'm sort of in some kind of controlled compact part, everything less than or equal to q. I'm ending less than or equal to q, so I'm back in my compact part again. But I'm spending most of my time outside the compact part. So you think about capital M as being really big. So the proportion of time in between the 0th step and the n plus first step that I'm in the compact part is very small. I'm spending most of my time being quite big. Okay, so then delta infinity top is, hopefully I get my limits in the right order in the right way. So there's lim, lim, lim. 1 over n log zn n q. So I take the lim sup in n, I take a limit in, sorry, capital M, this goes to infinity, and I take a limit in Q.
Sorry, Mike.
Yep.
I actually just saw a question in the chat from Alit at CB. Ali, do you want to just say it? Or he's asking, I think he refers to the top half. What can be said when all mu n are ergodic? I'm not sure.
I mean, the same result holds if mu n are ergodic or if they're not ergodic.
Right.
I don't know if, maybe you're asking something more sophisticated than this. Yeah.
You can ask.
You can say something more if they're all ergodic. I'm not sure, but certainly this theorem holds in the general case. I'm not sure if that's a good answer or not. Anyway, there it is. Okay, so this is my topological version. So, I mean, if you know about Gurevich pressure, so this is Gurevich entropy. So I'm not dealing with pressure, dealing with entropy. So in Gurevich entropy, it's the same kind of counting, but you don't do this kind of extra restriction that things are going off to infinity, right? So the total topological entropy would be computed without this condition on things going off to infinity. And also you wouldn't need to take this limit in Q either. You could just fix a Q and you get the Gurevich entropy. Okay, and so what we get is second theorem, which is variational principle. So this says that, well, the variational principle, which says that the topological version and the metric version are the same. And as I say, most of our work in the paper is using the topological version and doing lots of counting. In my example, non-semi-continuity. Sorry, right, okay, cool. Yeah, right. Okay, we'll talk about that at the end. Right, so yeah, so most of the stuff is doing with this counting. And so let me just give you a quick idea. So basic idea of proof of, oh, sorry, I should also mention that Boozy has a version like this. Boozy has similar idea. Right, okay, so basic idea of the proof of theorem 1. So you take, well, is to use the Katok entropy formula. So we want to count Bowen balls, right? That's the plan. So what you do is you take a finite partition, you take the one cylinders, one cylinder starting with 1, one cylinder starting with 2, and so on, up to k. This isn't quite what we do, but this is roughly what we do. And then you take the rest. Right, so you think about that as your initial partition. And so then you use the entropy formula. So the usual entropy formula, namely the formula that I showed in the beginning of the talk on mu to count Bowen balls. Required to cover the compact part. So namely the cylinders, whenever you're involving the cylinders 1 up to k, you can use the entropy formula to essentially count the number of Bowen balls you're going to need. And then use delta infinity to count balls required. Balls required to cover the non-compact part. So you break up your sequences into the bits that consist of the symbols here, and then the bits that consist of the symbols in here. And that sounds quite straightforward, but it's more complicated than that, of course. In the case of flows, this type of idea works quite nicely, because in flows, if you're going off to infinity, you can only go off to infinity in a very particular way. Whereas with shifts, you can jump to infinity, well, you can jump near infinity in one step quite easily. So here you need to kind of separate out things in a more complicated way, but I won't talk about that here. Okay, so it's a big counting argument. Okay, let me give you a couple more little results before I finish. So theorem 3 says that if delta infinity is less than the topological entropy of sigma, that implies that there exists a measure of maximum entropy. Okay. So this condition here which should be referred to as strong positive recurrence. So if you're, for example, aware of the work of Sarig, this is the kind of condition that corresponds to strong positive recurrence in the kind of work that he does. I should also mention Gurevich and Salama and people like that. This is actually very easy to prove, and also Boozy has a version of this. So this is an easy corollary of theorem 1. So the Gurevich variational principle implies that there exists some sequence mu n such that h mu n converges to the topological entropy of sigma. All right. So this is how you would kind of compute yourself a measure of maximum entropy. You would take a sequence of measures whose entropy converges to the topological entropy, and you would hope there would be a limit. Right, so you would hope that this sequence here would have a limit. So compactness of this space of subprobability measures in cylinder topology implies we may assume, after taking subsequences, that mu n converges in cylinder topology to mu, and star, i.e. the result from theorem 1, says that the lim sup of h mu n, which I've assumed is the topological entropy, is less than or equal to the total mass of mu, h of mu over the total mass of mu, plus 1 minus total mass of mu times delta infinity. Okay, and if delta infinity is strictly less than topological entropy, then the only way you can satisfy this inequality is if the total mass of mu is equal to 1. Okay, this implies total mass of mu is equal to 1. And so mu is actually a measure of maximum entropy. So mu is a measure of maximum entropy. Okay, so quite straightforward. Right, so that's one result. So lots of examples of strongly positive recurrent countable Markov shifts. But just to come back to my example, sigma SV isn't one of them. And it comes back to something that Stefan was saying in one of his questions, which is that because this thing looks the same all the way through, right? If I block out this symbol 1, then this is topologically exactly the same as what I had before, right? I have a full shift here, not full shift here, and so on. So if you block out the first n symbols, it looks the same. And using that idea, you can see that that the total entropy of the system is represented as far to the right as you want. Okay, I don't know if that makes sense. So if you delete the first n states, so no entropy is lost because you're topologically the same. So actually delta infinity is equal to the whole topological entropy. And in fact, this is equal to log 4 out of interest, so it is finite. Oh yeah, so none of this stuff works if entropy is infinite, because you can have a little bit of your system which is going off to infinity but with very big entropy. And if you're allowed to do that, then all this stuff breaks down. Okay, so in fact, in this case, there isn't an imaginary maximum entropy, although it's not an if and only if statement, is there? So there's no measure maximum entropy for sigma as phi. And let me just finish with a little theorem. There's lots of conclusions in this paper, but these are just a couple of them. So if there is not a measure maximum entropy, and mu n has the limit as n goes to infinity, h mu n is equal to topological entropy, then mu n converges on cylinders to 0, which is what you would expect, I would hope. So yeah, so that's how all this this concept of entropy at infinity all fits together. And yeah, I think I'll stop there. Thank you for your attention.
On behalf of everyone, thank you very much. A nice talk. Thank you. So I think we will I'll start with Ali's question. Then maybe if people want to ask a question, they can just type question, just the word question in the comments, and then I will go through the questions. Yes. So Ali was talking about your example.
Do you hear me?
Yeah.
Okay, thank you. Hi, how are you? So my question was, let me just, you made an example of a sequence of non-ergodic measures where they will escape the mass and the entropy, okay? So the silly question was whether the example can be ergodic sequence. So I was waiting in your theorem appearing some ergodicity, etc. But you said about the entropy at infinity. It is not clear for me if it rules out or it's including ergodic sequence. This was the question.
Yeah, no, that's a great question. And yeah, it's something I actually glossed over intentionally. But yeah, that's absolutely right. So I could make this example ergodic by some kind of small perturbation. So yeah, so I can make the examples where the non-semi-continuity fails to be ergodic examples if I wanted.
Is it clear, obvious perturbation you may?
No, but in this paper we also have, well, we probably don't need the full power of this, but in this paper we also have a statement about the density of ergodic measures. Yeah, okay. So that's one way of showing that.
Okay. Okay,
thank you very much. So I think Catherine and Lorenzo had a question.
Yes, I have a question. In your last slide, you have this theorem 3, where you see that there is a measure of maximal entropy, but do you know if there is a unique or you may have many or?
Yeah, you can have many. I mean, I can design examples where you have, well, if you give me a number, I can give you an example. I mean, for example, if you can go off to infinity in like n different directions,
yes,
with equal kind of complexity,
yes,
any measure in any of these directions will be a measure of maximum entropy.
But you have also have this example with infinitely many, or this is
yes, I think I can do that. Yes, I think I can do that. I mean, so finally many, for example, you know, you can have one, you have your shift going off in one direction, and then you just add on another shift going off in the other direction.
okay?
So, for example, this example I had in my talk, if I just glue on another version of it going to the left instead of to the right, that would be another infinity.
Okay, but this is
not transitive, right?
Sorry?
Not transitive.
Not transitive.
not ergodic.
You can make it transitive.
Sequence of
Yeah, you can tie it together and make it transitive. But yeah, okay, fair enough. Yeah.
Okay, well, thank you.
Simon Baker.
Hi, Mike. Hello.
Hi.
Hey. So I had a question about this example you had at the start when you had this measure, the sequence of measures nu n on 1 and n plus 1 on these three symbols. And I remember you said this example, you have this sequence converges to the zero measure when you have measures on with respect to convergence on cylinders. Right?
Sorry, I'm getting myself confused with what's going on Hannibal's comment. Say it again.
So at the start, you had this example of the sequence of measures which was supported on 1, n plus n and n plus 1, and this converged on cylinders to the zero measure, if I'm not mistaken.
Right, so I had the n. Yeah, I mean, okay, I can just draw it again. So I had n plus 1. So we're talking about this?
Yes, although I seem to okay, so I think when I first saw your drawing, I misunderstood it, and I thought it was on 1, n plus 1 and n plus 2.
No, sorry, yeah, it's just n.
Okay, but I think my question is still valid in that case, because there was this compactness result stated, and if it is on 1, n plus 1 and n plus 2, and you do have this compactness results that the sequence of measures will converge to something.
Yeah.
Then, to me, if I was to say, okay, what is the measure of the cylinder just containing the element? The cylinder given by the symbol 1.
Yeah.
Well, this is going to be independent of n. If you do have the 1 and n plus 1.
Yeah.
So that will be independent of n. So, in particular, I know this word would have positive measure. But then if I ask myself, okay, what is going to be the measure of the cylinder 1, 1? Well, this will be strictly less than 1. And any other word, say if I had 1, 2, this would have 0 measure, 1, 3 would have 0 measure. So I don't really see how one gets a reasonable measure in this case.
Yeah, you wouldn't be able to, yeah. I mean, you can.
But I thought it had to converge to something by this compactness result.
I mean, this you wouldn't be able to get an invariant measure which lived on which saw 1 here, right? Because there's no way of getting back to 1.
Well, I mean, why can't I just draw a line going? I mean, why don't we introduce an extra line which goes from n to 1?
Okay.
Then and yes, this has a measure of maximal entropy for each n, and this measure will give the word corresponding to the cylinder 1 a certain measure which will be independent of n.
Yeah.
But then if you were to say, okay, let's think of any cylinder of length 2 which began with 1, well, the measure given to 1, 1 will be independent of n, and it will be strictly less than the measure that is given just to 1. But if you were to take any other word like 1, 2, 1, 3, 1, 4, well, eventually these are all going to have 0 measure. If I think of this shift as lying in a countable shift. So I guess my point is I don't see how this sequence of measures could converge to anything reasonable, because it seems that the measure of the word one would have to equal the measure of the word one, but there's going to be a strict inequality here. Does this make sense?
Makes sense to me. I don't have a good answer. Maybe Hannibal has an
But what is the whole shift? You need to have like one shift, like the entire thing. You're not giving me the whole sigma. You're giving me a piece of sigma. I need to have sigma.
Yeah, I think.
I'm sorry, I don't see why. I mean, I could think of 1 and n plus 1 as lying in this much larger sigma.
Yeah, I think the issue is that, well, at least the thing that I was saying, which also worries me, is that if you're going to add these extra arrows to be able to get from n back to 1 from all the ends, then you're defining a new kind of
I
sequence.
think the entropy is infinite.
Yeah, exactly. And then
If you're going from 1 to n, then you have this loop like at n, right?
Yeah.
Okay.
So you can bootstrap. I mean, this is not going to have finite entropy.
Yeah.
Oh, okay. And the compactness was in a finite entropy case.
Actually, you don't need finite entropy, but you need to have finitely many periodic orbits of a given length, which is more
Okay.
like a topological condition, and you also don't have that here.
Oh, okay. All right. Sorry. I guess I didn't appreciate this detail. Thank you.
No, but that's okay. That, I think that clarified. That was interesting. Yeah. Interesting example. Interesting question. Yuli, you had a question?
Yes. Hi, Mike.
Hey.
So is there a relation between your work and the work of Shapira and Tapi on geodesic flows, where they also talk about entropy at infinity?
Again, since we have Hannibal here as an expert, I'm not such an expert on the geodesic flow setting. I mean, a lot of this stuff is inspired by the geodesic flow setting. I say most of the work that I've looked at is like Einsteiner, Kadyrov, Paul kind of people. But do you want to say something, Hannibal?
Sure. It's the same. I mean, you have the same quantity, but they are using it in a different way. So, I mean, they also define the entropy at infinity, but they are not looking at measures and sort of dissipation of measure. At least in the paper that they had, they are actually looking at changing the metric, and they are trying to see how the topological entropy change with that. And they noted that typically they cannot really control the perturbation unless they have this gap, which is the like strongly positive recurrent condition. But I would say that it's a different sort of setup. The same quantity show up, so it's pretty natural, like having like a gap with infinity that give you enough control typically. But I would say it's a different setup.
But for instance, if their geodesic flow has like a Markov partition, is induced by a Markov partition, is their result covered by your results?
Yes. Oh, right. So the thing that okay, maybe let me say what they prove. They prove that if you start with a metric, so that the metric is, has this gap, the delta infinity less than the topological entropy, then when you perturb, then the topological entropy moves C1. Of course, if you have a Markov partition, then when you perturb, you can think of having a reparametrization of the flow, which is also what they are trying to do. But if you have the Markov partition, you can actually have like a larger class of perturbation. You don't need to really perturb a metric, you can perturb the dynamical system. So if you have a Markov partition, you can improve the result. But since we don't have the Markov partition, the result is the best possible. And they are not using any Markov partition.
Okay, maybe I will just, we're going on, but let me just ask a kind of a general question, Mike, is can you kind of translate this into results for the interval map, for example, that you were, used as an example to construct the shift? I've always been a bit puzzled about this when you have this, because the interval is a compact space, the shift is non-compact, but is there an obvious way to 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 formulate this result just without reference to the infinite subshifter as a result about measures for the interval map that you described?
I think in this case, yes. But in general, I mean, when we first proved this, we hoped that it had more applicability, for example, for any kind of system you can code.
Mm-hmm.
But in fact, you need to be careful, this was pointed out to us, you need to be careful how the coding, whether the coding preserves the topology.
The coding what?
Whether it preserves the topology.
Ah, so the connection between the topology of the space and how the coding works.
Yeah, yeah.
So in this case, you have a kind of monotonicity in some sense. In this case, is that why you say it applies? Because you've got a simple coding with just one accumulation point and so on. I mean,
I'm not sure why I say it works in this case.
the measure that goes to infinity corresponds to converging to the fixed point at 1? Or?
Yeah. I mean, it's kind of a funny way to do this problem, actually, to code and then go back, because yeah, I think I'm not sure, but I think you can understand how the projection works in this particular case. I'm not totally sure about that, but I think that's true. Whereas in a general case, it's you take a sequence of, for example, for surface diffeomorphism that Omri can code, then you take some weak star limit of measures and stuff. That doesn't necessarily correspond to the converging on cylinders for the coded system, which is an issue.
But so, for example, could you tell just by looking at the one-dimensional map that you do that it does not have the strong positive recurrence condition without looking at the coding? I mean, can you see it as a feature in the map? But you need to go to the coding first and look at the transition matrix.
I mean, as I say, the thing is, I mean, when you look at it, I'm kind of looking at the coding at the same time, because
I know it's hard to
using the market properties of this guy, and that's a good thing. But as I said in the talk, if you kind of block off the first few branches, your map looks the same topologically. Therefore, you can see that the entropy has to be any kind of measure of maximum entropy candidate would have to converge to the Dirac mass of 0, basically.
Okay, thank you. Are there any other questions? Wait, there's one mess. No. Any other questions? No. Okay, well, thank you so much, Mike. It was a very interesting talk. Let's thank Mike again. And back to Lorenzo, I think, to close up the session. And